This is section 3.4, zeros of polynomial functions. Now, there are a lot of different pieces to this section. We're going to have several different theorems, and it's might be frustrating to you because there is not a single linear path to solving these problems. There are a lot of different routes, and I can't give you a definite way to get through these. So we have a lot to unpack here. Just be patient. Where we are going is to where we can solve any kind of polynomial equation. So far, we can solve any quadratic, and then we can solve other things if they are in a specific form. So if they're a quadratic in form, we can solve those. If they happen to be able to be factored by grouping, we can solve those. But in general, we cannot solve a polynomial equation yet. Okay. So the first thing we're going to do is we're going to talk about the rational zero theorem. Okay. Rational numbers are numbers that can be written as a fraction. So examples of rational numbers would be things like, all right, 2 is rational because I could write it as 2 over 1. I could write 2/3. That's rational. -5 is also rational because I could put that over 1. And then the one that we're not going to see too much in this context, but that is if you have a decimal that is repeating. A decimal that is repeating, or also a decimal that ends. Those are also rationals because we could write these as fractions. The one thing we cannot deal with rational zeros, well, we're not going to end up with decimals that never end or never repeat. Now for us, that usually means a square root of a number that's not a perfect square. It also is not going to give us complex answers. So any answer that involves an I, we're not going to get from this. So it has some limitations. If we have a polynomial function, you've seen this before, just the general definition of a polynomial function. If it has integer coefficients, this is important, okay? What this means is we have no fractions. We are only allowed for our coefficients to be -3, 5, 10, things like that. No fractions at all. Okay, so if we have a polynomial function where all of the coefficients are integers, then we are going to be able to use this theorem in order to create a list of potential zeros. And the way we do that is we're going to be able to look at our last number here, which is a naught in a UGHT. You may remember from a previous section. A naught is going to give us all of the possible values for a numerator. Okay? And don't worry about this all too much now. We're going to work some problems like this. It's going to make more sense once we have an example behind us. And then the denominator, we're going to be able to figure out from our leading coefficient, whatever it is. So we're going to be able to create a list of a whole bunch of fraction type answers that are possible answers to our equation. So basically, we're going to be able to take the idea that we have, well, if I just glance at this, I have an infinite number of possibilities that I can think of without trying to work it. That's an infinite number of possible answers. We're going to be able to use this theorem to be able to create a finite list of potential answers. It may still be a long list, but going from infinite to finite is always good. Okay? This is going to generate a list of potential zeros, and we're going to need to check them all, and we're going to use synthetic division. Okay? We're not just going to plug in our potential answers and see if they work. And the reason for that is, let's say that I'm working the problem and I find that -3 is a solution. I plug in -3 and it works out. What I will not be able to tell is whether I got -3 as an answer just once, or if it had multiplicity 2 or 10. If I'm not using synthetic division, I'm not going to be able to tell that. So we really need to be using synthetic division, okay? And this is what I was saying before, okay? It only applies if the original polynomial has integer coefficients, no fractions allowed. And notice the theorem only generates potential rational zeros. So again, it's not going to give us any potential answer that still has a square root in it. It's not going to give us any potential answer that still has an I in it. Okay, so we have limitations. All right, so for this first problem, we are asked to list all potential zeros of the given polynomial function. We're not asked to solve it. We're just asked to generate the list of possibilities. Okay, this is A naught. So our A naught is -8. And our A sub n, which is our leading coefficient, is the coefficient right here. So our A sub n is 1. If you look up here, we need to find P's and Q's. The P comes from A naught. And what is P? It is a factor of the constant term. What that means is I need to figure out all of the numbers that divide evenly into whatever this is. Okay, so since P comes from -8, we don't really have to worry about our sign here, because if I'm looking for things that divide evenly into 8 or -8, the first possibility is a 1, and I can do plus or minus 1. Both 1 and -1 divide evenly into -8. Then plus and minus 2. That's the next largest thing that divides evenly into -8. It's always going to be plus or minus. That's why you don't have to worry too much about the sign here. Okay? 3 does not divide evenly into 8. 4 does. So plus or minus 4. And then the next one that works, not 5, 6, 7, the next one that works will be 8. So what I have just found is that if I'm going and list all of the possible answers, I'm going to have to cycle through all of these numerators because that's where my P is. Okay, now Q comes from all of the possible numbers that divide evenly into your leading coefficient. Now our leading coefficient here is 1, so the only numbers that divide evenly into 1 are plus and minus 1. Okay, so if I'm just going to list my potential zeros, those are all of the P over Q possibilities. And what you want to do, now granted my Q I only have one possibility, but as you're doing these you want to establish a pattern so that you don't miss anything. P over Q, I could have, again, it's always going to be plus or minus, so you don't really have to worry about the signs, just remember plus and minus. 1 over 1 is 1. Plus or minus 2 over 1 is 2. Plus or minus 4 over 1 is 4. Plus or minus 8 over 1, which is 8. Now again, I'm not actually solving this, but I went from just glancing at this and having an infinite number of possible answers, and then used this theorem and got it down to just 8 potential answers, which is pretty good. Okay, so let's work this one as well. Again, I want to list all of my potential answers, just we're not worried about finding it. Okay, my A naught is 2, and my A sub n, or my leading coefficient, is 4. My P values are everything that divide evenly into A naught, our last number. So that would be plus or minus 1, and then plus or minus 2. Q. This would be all of the values that divide evenly into 4. So that would be plus or minus 1, plus or minus 2, and plus or minus 4. So I have more denominator options this time, whereas up here I only had 1. Now if I go to list P over Q, I'm going to set up a pattern and I'm just going to follow it. Okay, so 1 over 1 is 1. 1 over 2, again always plus and minus, that's 1/2. 1 over 4. Okay. Now, the next thing is when you go and you start creating more fractions. I've used this as the numerator for all of these denominators. Now I'm going to the 2. Often, the more fractions you generate, you're going to see that they reduce to the same thing. So I have right here 2 over 1, which is plus and minus 2. But then when I do 2 over 2, well, 2 over 2 is 1, and I already have 1 listed. And then I have 2 over 4, and that reduces to 1/2, so it's already listed. So right here, I have my list of potential answers for this polynomial function. And when we're asked to find zeros, what we're actually asking is, if you set this thing equal to 0, what would solve it? Or if you're thinking in terms of graphing, what are your x-intercepts? Where do you cross the x-axis?